So let's talk about birefringence. So birefringence is a phenomenon that happens when you shine light through an object and non-polarizing light through an object, creating two polarized rays of light, right? So how does that happen? That happens when, like I said, non-polarized lights hit the surface of a birefringing material. So there aren't any birefringing material. So I know that ice is one of them. There aren't a lot of birefringing material, and they all have, like, I guess, index of refraction. They have different index of birefringence. So once it hits, it creates two rays of polarization, so parallel polarization and perpendicular polarization, right? And these polarized rays will have different speed and they will diverge into the crystal. So that is one way of seeing birefringence. One of the ways to see birefringence is the way I see, not only the way I see it, but it's the way I did it for this 3-star. So I took ice and I took plastic, right? Hard, heated, molded plastic. These two materials are birefringing material. Ice and plastic do not have high index of birefringence. So for example, if we happen to take a laser and shine it through, we wouldn't see two dots at the end because the index is so small. You'll have to be a container this large, right? So so for the plastic, I took one sheet of polarized sheet, yeah, and put it in front of this plastic container. And I don't know if you can see, but you should see some different colors you didn't see with your eyes alone before. So what happened here is that the polarized rays coming from the plastic passed through this and therefore transformed it into visual light that you can see. So if we go more in depth about this phenomenon, here the light, when plastic is heated and stretched and molded, you'll have different density of material, so each place will have a different density, some place more solid than others. So for example, I know this corner here is really solid compared to this center here, it's just the ways things are. So engineers use this technique to see which part of the Tupperware, in this case, is most likely to break depending on the color, So when light hits, it travels in the container at different speed in each zone and creating colors that we can't see with the eye alone. This is why I'm using polarized sheet. And I guess that when the polarized light travels at higher speed and the container, its frequency is higher, and when it travels at slower speed, its frequency is lower. And just like that, you can see the spectrum of non-visible light. After that, engineers can say, okay, so for example, if the container contains, if we see any mark of, orange in the container, that means this container is more likely to break, like, on that spot. So I did the experiment also with ice. So I took a thin piece of ice, and I flipped my laptop over, putting the screen on the table and putting a white screen. I put one polarized sheet on the table, put the ice, and put another polarizing sheet on the table. So by doing such, as you already know, I'm blocking all the light like that, and I'm letting through most of the light like that. So what happened here is that the light, right, polarized light in this case, because the light was coming from the screen and there were a polarized sheet on the screen, it hit the ice and because of ice, H2O is water, and ice, there's a lot of bubbles, there's a lot of oxygen in water, there's a lot of carbon dioxide. There's a lot of cracks in the ice. You know, I don't have perfectly ice, like perfectly frozen ice. You know, so that's why light in the ice was traveling at different speed. So in the cavities, it was traveling at higher speed. In more dense region, it was traveling at, you know, slower speed. And the rays that were traveling at different speed were polarized rays, were rays that without these, I wouldn't be able to see in the eye. So that is why when I put the different sheets, I can see the different colors shining into the ice, you know, the different colors showing me cavities, showing me bubbles, showing me place where the ice have cracks, place where the light shines at different speed, travels at different speed into the ice. So I will put both of the video of me showing birefringence in plastic and birefringence in ice at the end of this video. I hope that satisfies you, and to be honest, I learned a lot about this phenomenon. I mean, it's pretty crazy that we can see just like how strong is a material in every place just by putting the polarized sheet before it, you know. So that's all. I hope you have a great day, and thank you for listening. So this is me doing the experiment. So this is the white screen I used as well as the Tupperware I used. So as you can see, when I put a polarizing sheet before it, I can see a lot of lights. And by changing shape, this is really like a polarizing filter. So I change like the type of light I want to receive and I want to receive into my eye. And that is why when I put it 90 degrees, most of the visible lights gets, you know, turned down. So this is me doing the same experiment but with ice. So as you can see, I'm using two polarized sheets here to better see the color, because the index of birefringence of ice is really small. As you can see, when I turn both sheets, colors are changing place, and it's because I'm changing the shape of, you know, I'm changing the shape of the filter, and by changing the shape of the filter, I'm changing nevertheless the lights I'm receiving from the screen and the lights that is emitted. The same light is always emitted from the ice, but when I change the filter, I change the light I want to receive. So this is why colors are changing, because I'm changing the light I'm receiving, you know. So thank you for listening once again.